Have you ever noticed how two things made from the same parts can act completely different based on how those parts are put together? Think of a puzzle or a Lego. You may use the same pieces, but if they arrange it differently, you get a totally different picture or figure. In chemistry, it's the same. Molecules with the same atoms can have very different behaviors just because of their shape. Today, we are focusing on how to describe and understand those shapes, especially in terms of cis and trans isomerism, because that's the main topic for today. The agenda of the presentation looks like this. We're going to introduce you to the information, then discuss importance of cis and trans isomerism, give extra information about E and Z nomenclature, and of course in the end conclude and give you references, the information we took from which. Now let's focus on double bonds. A double bond is like a rigid connection between two atoms, preventing them from rotating freely. This rigidity opens up the possibility for different spatial arrangement of the atoms attaching to these carbons. What do I mean? When two identical groups or similar groups on the same side, that's cis, and when they are on different sides, that's trans. You may ask, and how to identify sides of the double bond? Imagine that a double bond is a plane. So if the groups are above this plane, it is a cis, and if they are, and some of them are below, that means that it is trans. The importance of these structures in the chemistry? They may have different solubilities, they may have different boiling points and melting points. We can implement this knowledge in the different domains, for example, in the food industry, of course in the medicine, in the laboratories, and also in the production of some resins and so on. We will dive in this topic a little bit more further in this presentation, and for now I want to give the word for the next speaker who will tell us more about cis and trans isomerism.
So, what is cis and the trans isomer? At the most basic level, cis and the trans are labels that tell us about the spatial arrangements of atoms in a molecule. Think of it as a molecule's 3D puzzle. We are not just looking at what pieces are there, but how they fit together in space. A cis isomer is like when two important pieces of the puzzle are on the same side of a double bond or a ring. It's like saying these two things are next to each other. A trans isomer is when those pieces are on opposite sides or across from each other. It's crucial to understand that this isn't just a naming game. The arrangement of atoms affects the molecule's overall shape, which in turn affects how it interacts with other molecules. Think of it like a handshake. If your hand is in the right position, you can shake hands. If it's not, you can't. The same goes for molecules. The shape determines if they can shake hands with other molecules, which affects their properties. Conditions cis trans isomerism. But not every molecule can have cis and trans forms. There are specific conditions that have to be met. First, this type of isomerism usually occurs in molecules with double bonds or rings. Double bonds are like strong, rigid connections between two atoms, and the rings are closed structures. Second, the molecules need to be locked in this shape. Double bonds can't rotate, which means the atoms attached to them stay in their positions. Rings also keep the atoms in a fixed arrangement. If the molecule could easily twist or rotate, it wouldn't have stable cis or trans forms. It would constantly change between them. Third, and this is really important, the groups attached to the double bond or ring need to be different. If you have two of the same group on the one side, there is no way to have a cis or trans arrangement. For example, if you have two hydrogen atoms on one carbon of a double bond, it doesn't matter what's on the other carbon, there won't be cis or trans isomerism. You need two different groups on each carbon of the double bond or on the relevant carbons of the ring to create this spatial difference. To give you a clear picture, imagine a seesaw. If you put two identical weights on one side, it won't tilt either way. You need different weights to make it tilt. Similarly, you need different groups attached to the double bond or ring to create the cis and the trans arrangement. Examples of cis-trans isomerism. Let's look at some more detailed examples. 2-butene is a classic one. It has a double bond between the second and the third carbon atoms. If the two methyl groups are on the same side of the double bond, it's cis-2-butene. If they are on opposite sides, it's trans-2-butene. The cis version might have a slightly higher boiling point than the trans version because of how the molecules pack together and they interact. Another good example is malic acid and fumaric acid. They have the same chemical formula, but malic acid is the cis isomer and fumaric acid is the trans isomer. Malic acid is more soluble in water than fumaric acid because of how their shapes affect their interactions with water molecules. This difference in solubility is a direct result of their cis-trans isomerism. Understanding these examples helps us see how cis and the trans isomerism is not just a theoretical concept, but a real phenomenon that affects the properties and the behaviors of molecules in many different contexts. Now that we know how to identify cis and the trans isomerism, let's discuss the real-world applications.
Now that we have covered the definitions and the conditions of cis and trans isomers, let's explore their real-world impact in industries, pharmaceuticals and drug development. Importance in industry. Cis and trans isomerism plays a major role in industry applications, especially in the food industry. You have probably heard of different types of fats. Cis fats found in food like olive oil are considered healthier. This cis configuration creates a bend in the fatty acid chain, keeping them liquid at the room temperature. In contrast, trans fats produced through hydrogenation have straighter chains that pack tightly, making them solid. This increases shelf life but also raises health concerns, which is why nutritionists recommend limiting trans fat intake. Another example is polymers. Natural rubber of cis polysaccharide is flexible and elastic because this configuration allows polymer chains to slide past each other. However, trans polysaccharide is gut-friction is rich due to tightly patched structure. This difference directly results from cis-trans isomerism. Now let's talk about role in pharmaceuticals. In medicine, the distinction between cis and trans isomers is critical. A well-known example is cisplatin, a hematography drug that effectively binds to cancer cell DNA. However, its isomer, transplatin, has the same formula but is completely inactive, showing how molecular shape affects drug function. Another example, vitamin A, retinol. Vision. Light absorption in the eye involves the conversion of cis-retinol to trans-retinol, triggering signals to the brain. This highlights how the isomerism plays a role in essential biological functions. Then impact in drug development in drug development. This specific isomers from a drug is crucial for effectiveness. Many drugs interact with biological molecules like enzymes, receptors, and their 3D shapes determine how they will bind. A cis isomer might be retinal, while a trans isomer could be inactive, even harmful. Be careful selecting the correct isomer. Drug developers issue better treatment with fewer side effects. How the food we eat to medicines we take cis and trans isomerism has a major impact on daily life and is scientific advice. And understanding these concepts is essential for various industries. Now I will pass it to fourth speaker who will discuss how we apply this knowledge and the different areas of chemistry.
Cis trans nomenclature is effective for simple alkenes with two different groups on each carbon of the double bond. However, it fails when we encounter alkenes with 3 or 4 different substituents. This is where the AZ system becomes indispensable. The AZ system employs the Kahn-Ingold rules, priority rules, assigning priorities to substituents based on atomic number. If the higher priority groups are on the opposite sides of the double bond, we design it as the molecule as E. If they are on the same side, we designate it as a Z. Either one bromo, one chloropropene. Cis trans nomenclature is ambiguous here because we have 4 different groups: bromine, chlorine, and methyl and hydrogen. To accurately describe this molecule, we use the AZ system. In one bromo, one chloropropene, bromine, atomic number 35, has higher priority than chlorine, atomic number 17, and the methyl group has higher priority than the hydrogen. If the bromine and methyl groups are on the opposite sides, it's the E isomer. If they are on the same side, it's Z isomer. Another example, 2-chloro-2-pentene. And here we cannot use cis trans because one carbon of the double bond has a chlorine and a methyl group, while the other carbon has ethyl group and hydrogen. Using AZ, we assign priorities if the chlorine and ethyl are on the same side, it's the Z isomer. If they are on opposite sides, it's the E isomer. The AZ system ensures unambiguous communication stoichiometry, which is crucial in organic design, where even subtle differences in spatial arrangement can significantly impact the molecular properties and reactivity. Why this matters for chemistry students? Understanding isomerism is fundamental for chemistry students in organic synthesis, meaning reactions are specific, producing a specific isomer. Controlling stoichiometry allows us to synthesize complex molecules with the desired traits. Moreover, many reactions are influenced by reactant stoichiometry. The cis and trans configuration can affect reaction rate, product distribution, and reaction feasibility. For example, a reaction might proceed favorably with cis reactant but not with the trans reactant, or vice versa. The spatial arrangement of atoms can influence how molecules interact during a reaction. In summary, cis and trans nomenclature is fundamental tool for distinguishing molecules with identical molecular formulas but different spatial arrangement. It has profound implications across various fields. We've explored how it influences the properties of fats, polymers, and the pharmaceuticals. So this is our reference that we use in this presentation. So thank you